All right, we'll get started. Don't want to hold you guys up any longer than you have scheduled for this. Again, my name is Laura Horseman. I want to thank you all for attending. Today, we're going to cover our best practices, starting with chapters 9 and 10. We're getting towards the end of this series within our ABU Online Design Professional series. Um, Today, for chapters 9 and 10, we're going to be covering global stability and terraces. You guys are on listen only mode, so if you guys do have any questions, feel free to stick them in the chat box or the questions answer area, and I'll answer them hopefully as I go. If not, I'll catch them at the end. So let's get started. Again, my name is Laura Horseman. I'm one of the engineers here, and we'll get started right here on what our objectives are for this webinar today. Starting with the objectives, we want to cover what and why is best practices. Why do we have it? What is it? And why is it important? Then we're going to go right into the global stability and terrace applications of how to identify concerns, how do you solve any global instabilities, and then how to determine if it's a terrace application and how to design for them. And then also global stability in regards to them as well. All right. Again, if you have any questions, feel free to ask them in that question area. So, best practices. What is it? It is a industry-wide initiative to aim for zero wall failure. How we can determine to get to zero wall failure is after investigating failed walls. Uh, we have found what some good guidelines, some tricks and tips, and best practices, hence the name, of how to properly design and install retaining walls. And one of the first things that we noticed, first things that we term as being very important, is getting that design out of the contractor's hands and back into engineers' hands before it goes out to bid. And why do we want to do that, and who should be responsible? Who we think should be responsible for that wall design would be ideally the project site civil engineer, mainly because they have control or more control of what's happening on site. So if as they're designing that retaining wall, they come up with utilities that are in the wrong area, they need more space for the wall due to its height, they have to worry about property lines and whatnot, they have a little bit more control to adjust those to get their wall design to work. Not saying structurals, geotechs, and others couldn't do it. They're just the ideal person. I know that in the States here, there's a couple of areas where only civils can design it and only structurals can design it. So it all depends on your local municipalities and counties how they want you to do it. But we do say the site civils usually have a little bit more control. So take that with a grain of salt, and however your areas do it, local reigns supreme on these. But that's who we would prefer to see it, mainly just out of the contractor's hands. All right. And why is it important? If we have it designed before it gets to the contractor, before it gets to bidding, you've already thought out of everything that could potentially go wrong, hopefully. So hopefully you can avoid any failures because you've accounted for everything. You've minimized delays because you've noticed any complications before it got there. And you're eliminating oversights because you've seen them as you're designing the walls before it goes out to bid. You're accounting for it before it even goes out, so you're eliminating that potential. All right. So before we dive straight into talking of global stability, I have a little video here. That's a video of a slope failure, an intense one in Japan. So let me get that playing. As you can see the full fallout. There was some retaining walls and road structures on there, and so no matter how well those were designed, it was the slope that gave way, not those designed. You could also notice that when some of those trees were coming down, they were coming perfectly vertical, how they're supposed to be on the hillside, and they just came down with the slope. So that means it was a deeper failure than just surface or the wall. All right. Gave us a little taste of it. So, what is global stability? We have a definition here. Global stability, slope stability, or site stability, those usually are interchangeable depending on their use, but it's the overall stability of the slope or the site of your project. Um, it could be just a small focused thing, or it could be the larger scheme of things depending on the scale of your project. But the minute definition, or the more pointed for us, is the rotation of the entire soil mass. So it's slope, site, whatever, how it, you may have designed it perfectly, and this is how it was installed, but something may have changed and it slipped. A slope stability, global stability. And as you see, it wasn't within the wall, it was beyond it. So that's saying no matter how well you designed that retaining wall, it was the surface or the global stability that was the problem, not the wall design. So that's why we always want you to, based off of your conditions, your projects, whatever you have on there, um, consider, is global stability going to affect my design? And now we're going to show you how you can change your design or what to look for so that way you can get to a safe and stable site. All right. First, here's a quick pictorial line art description of a global or slope failure. The slope was originally pretty consistent, but some changing parameter, be it a rainstorm or water event, changed the stability of the soil. Maybe it was a seismic event. Maybe it was deforestation. Maybe it was somebody dug out the foot of this wall, making the upper area just slide down to come back to equilibrium. There's a lot of different factors into why a slope could fail. It is our jobs as engineers to predict or determine how best to counteract any of those to make sure that slope stays in place. All right, so here's some pictures of some slope failures. The first one, the far left, is showing you a massive slope failure, just like we saw in the video. So it could be quite significant, causing many days and delays, costs and expenses because you have to clear that, then you have to rebuild, move all of that stuff out of the way, make sure the road is still stable. So there are some pretty significant factors. So that's why something as a site project you always want to pay attention to, but it also could be really small for like a small residential backyard. They had a slope, there was a heavy rains, and they had a what the engineer owner of this house called a landslide. When I thought landslide, I thought huge, massive project. No, it's a small one, but it is still significant and still labeled as a global stability or global failure. So you also have to take that into account for even small walls too. It's not just big ones or certain conditions. You also have to pay attention to what could potentially happen even on a small wall. I knew an engineer that I helped design a wall. He had a 3 foot tall wall with a small slope above. So I thought, oh, this should be no problem. But he also had a tall residential apartment complex above that wall, really close to it. And when I ran a global analysis, his standard wall, the small little 3 foot wall, did not pass global stability. So it could be a whole range of large or small walls. So always pay attention to what's happening on your site and what could lead towards a global. All right. So, as I mentioned, what is a concern, or what do you need to look for on your site to see if it is a global concern? Tall walls is a big indicator. If you've got a tall wall, you've probably adjusted that site, added more to it. You got to make sure that the foundation soils can handle that. We'll cover a little bit more of that here, but that was also covered in Chapter 8 of Best Practices, which was our last webinar last month. If you missed it and you would like to see it, I can send you a video of that presentation last month. Just let me know. All right, so today we'll dive into slopes, uh, poor soils, surcharges, and terraced walls as part of our section here. Hold on just a second. I had to use my cough button. And we're going to be diving into chapters 9 and 10 to cover this. So let's just get right into it, starting with Chapter 8 as a quick review for tall walls. The overall stability of tall walls must be considered separately from standard wall designs. So that could mean you might be, as the wall engineer, assigned to design the wall itself, and that's mainly just probably involves the design envelope, which I'll just define here in a minute. Otherwise, if you are the geotech or the site civil on the project, you might go beyond that. However, with the tall wall, it is a separate calculation. You can't just consider it all in one. You do have to consider if global stability is going to be a concern. And how do you determine that? In some cases, internal compound stability. That is a modified Bishop's analysis that we have available in our AB Walls design software that will calculate some more in-depth internal calculations. And when you run ICS, it gives you a warning if more than 50% of the slip arcs are originating behind the design envelope. That kind of hints at a potential global stability problem. So you always should, when you see that message, just pause, think, do I need to investigate this further for global stability? As the engineer of record, that is your decision. And if you decide that that is something that needs to be analyzed or officially looked at, recommended that you talk to the owner of the project to let them know so that they can contact their geotech or contract a new one. It's up to them how they handle that, but you need to identify if that is an issue. All right, so now going into chapter 9, talking about global stability. If you guys have not seen our best practices document, we have it laid out that it starts off with typical details that have notes for every little aspect that we have in our in-depth chapters later on. So you can get a quick reference or a quick checkpoint. If you just needed a quick reference, you can see it right here in the typical details. But then if you need to go a little bit more in depth, find out what we're talking about, you can go straight to the chapter itself farther back, which we'll dive into right now. So starting in chapter 9, you have a slope below the wall. We're going to really have to talk about the wall embedment. Standard wall embedment for if you had flat level wall in front, level grade below the wall, you have a standard 1 inch per foot of wall height embedded. With a slope below the wall, you are missing most of that soil, so now you have to embed a little bit more so you can prevent any undermining, and then you can also assure that you have proper stability of that soil. So what we recommend, or what local ordinances have recommended, is that you have at least a 5 to 7 foot minimum bench from the toe of the wall to the crest of the slope. This allows you to get that extra embedment, and it'll the failure or bearing capacity of the soil is now fully underneath that wall. Less chance for undermining. Now, with that, once you've got your 5 foot level bench, then you start with the standard conventional, adding that 1 inch per foot of wall height, as we say right here on the left. So, for an example, if you have a 6 foot wall or a 2 meter wall with a 2-to-1 slope below the wall, you're looking at, for that 6 meter or 2 meter, 6 foot or 2 meter tall wall, you're going to have about 6 inches buried. That's following standard convention. Then if you've got that 2-to-1 slope below the wall, you now need to consider that buried, and to do similar triangles, get the 2-to-1 to that 5 foot bench, you're looking at about 2.5 feet buried just on that wall alone. So when you add those two together, you're looking at a total of 3 feet or 1 meter buried for a 2-to-1 slope below this wall. That is pretty significant when you look at it. That's an added 50% of your wall. So you're looking at a total of a 9 foot tall wall instead of just a 6 foot exposed. So if you have it left it up to the contractor and they don't know about this, that's a lot of blocks that they didn't account for, wall that was not designed properly, and essential pieces missing from a design. So it's always good to get this done before it gets to a contractor so everything is accounted for. All right. So then moving on to point B. In general, when a slope is below the wall, a slope below the wall is present, that is one of the key factors in kind of hinting at a global stability. So you should always check how severe is that slope below the wall? How long does it run? Is it significant? How much are you bearing? That sort of thing. All of those tie into, is this a global stability concern? And that's using your engineering judgment, your knowledge of the site, and the materials used to determine if that is the case. All right. So what happens if you determined that if you have determined that global stability is required on this site, or it should be looked at, and it's not part of your scope of work? What do? The first step is to guarantee or establish, do you need to do a global stability analysis? If the answer is yes, you let the owner know so that they can contract to a geotech or somebody else to do that global stability. If you are the geotech on site, perfect. Still let the owner know just in case they need to, you guys need to work out anything changing to your contract or your scope. So always let them know that there might be something additional happening. Um, if you have any questions on that or need any assistance, let us know. We'd be happy to walk you through in depth on each individual piece here. All right, I'm going to take a pause here for a second. I've got someone saying they don't have any visuals. Can anybody else see my screen, or is everybody else black? Please let me know in the question box. All right, somebody has visual. Um, Ricardo, sorry to say, if you don't have visual, I will send you the video link in my follow-up email tomorrow, and it will have visuals on there for you, so you can always check it there. I'll also send you a PDF of the presentation, so that way you can always refer back to what I said and flip through and see if you can piece everything together. Otherwise, feel free to give me a call. Thank you guys for letting me know that you do have visuals. If there's anything else that's missing, sound or something, let me know. All right, so we'll keep moving on here. All right. So once you determine that global stability should be run, how did you determine that? I've probably mentioned this multiple times. Our best practices is a little bit redundant just because it is meant to be a quick reference guide, not necessarily an entire manual. So if you were just looking for one thing, we made it easily accessible for everything. So just a quick run through conditions that could hint to a global stability analysis. Walls with slopes above and below the wall, poor soils. I mentioned it for the tall walls. There might be that 50% ICS slip arc warning in AB walls, which I have images here. So if you do run ICS for your retaining wall in AB walls, if it's going to hint at a global stability, you will get this pop up. More than 50% of the slip arcs at the back of the envelope could mean a global stability problem. This does not mean you have to run a global stability. It's not demanding that you do one. It's just letting you know, based off of these conditions, it should be looked at, but as you are the engineer of record, it is your decision and your expertise which is going to drive whether it is a global stability issue. So once you've accepted that parameter usually happens when all of the slip arcs are at the top and back of the design envelope. So if they all kind of meet together at the top back of the wall, that's kind of hinting at that's when that warning will show up. And then another condition to pay attention to is groundwater. So let's go into those individually. We've already covered the slopes below the wall. If you have a slope above the wall and you've just put the wall in the middle of that slope, you've now changed the overall aspect of that wall. It's essentially you've cut out the toe of that slope, so you just want to check and see if your retaining wall is sufficient enough to hold up that wall now that you've removed that toe. So always pay attention to what you're doing to the overall site when you're throwing in walls. All right, so let's go into here, poor soils. Just like standard retaining walls designs, if you've got poor soils, it's going to affect how it happens, uh, specifically for global stability. So if you've got clays, silts, poorly graded sands, expansive clays, or soils that range depending on their PI and plasticity index and liquid limits, LLs, that will all depend and vary on your soils, but those will all play a big role in global stability and retaining wall designs. Um, we have laid out in Chapter 6 the appropriate or accept allowable infill soils. That was a previous webinar also in this series. If you want, we can send you that one as well. But we do have it laid out here, like I said, redundancy. Infill soils must meet or exceed the design friction angle, described as noted in the cross section. So everything that you've designed for should be what's installed. If they are different, you should be notified, and maybe you have to rerun a calculation to a new analysis to just check and see if it's still appropriate. But some key pieces to look for is the soil must be free of debris. Makes sense. And then it also can consist of inorganic soil types like we have listed here. And again, that's all referenced and in more depth in Chapter 6. All right. So diving into the ICS, where walls are more than 50% behind, slip arcs are behind the back of the wall envelope. That is if you're using AB walls. But what is ICS? ICS is internal compound stability. It's a modified Bishop's analysis that calculates the safety factors of the slip surfaces that pass through the retained soil and the reinforced or your grid zone soil. That's just giving you a better knowledge or an in-depth look of what's happening for your internal stability calculations. We do have an entire chapter of that laid out in our engineering manual. I'll be sending you guys a link to that if you don't already have it in my follow-up email tomorrow. Um, Okay. Now, I've thrown out the word design envelope a lot, and I'll throw it out a little bit more later. But just to define what that is, the design envelope consists of everything above the base material of your retaining wall and back to twice the height, or if you've got a slope, the effective height, which is HE, plus the length of your geogrid. So whichever one's greater, that's going to be your design envelope. So when you run ICS in AB walls, this separate screen will show up giving you all the parameters that it's highlighting. So here's a picture on the right detailing the design envelope, so twice the height or the effective height plus the length and everything above the base material. So this is what ICS is going to do. Is it's going to find the worst case slip surface for every course of block based off of so many iterations. I believe this one ran over 62,000 iterations to determine those. And so when you hit hide in AB walls after you've run that calculation, those iterations will always change depending on the size of your wall. They will display the worst case slip arcs on your screen. So if they were to be below the minimums, safety factor minimums, they would highlight red, and you could have a visual representation of where that slip surface is and where it would potentially fail for that wall. So you can find ways to fix and solve it so that way you don't have that problem. All right. Last thing to look for, or it's a big thing to look for, is groundwater. Water is the number one enemy of retaining walls. That's why we try and design without it, keep everything dry. Most wall failures, the two key factors in a wall failure is either water management was done poorly or there was not as much compaction as required. So what we're dealing here with groundwater is if groundwater is within 66% of the height of your wall, from the bottom of it anyway, you potentially have a global stability concern because water does change the parameters or materials of the soils you're working with. It likes to change the soils, so that always depends on how much water, how consistent it is it always there? Does it fluctuate? Do you have a high water table, low water table? All that. It all adds into it. So when you do see that within the 66% of the height of the wall, below the wall, you should look to see if you've got global stability concerns by first deep failures and also compound failures, because it could be both. It's always good to check. All right. So you've run an analysis and you found out that your global stability safety factor is below the minimum. What is the minimum? I do believe the minimum for global stability for static situations is 1.3. I've also heard people say it's 1.5 or 1 or 2. That all depends on your comfortability. I do believe, though, the absolute minimum is 1.3. As for seismic considerations, I have seen 1.1 as the minimum. That's pretty been the consensus, but I'm pretty sure there's a range in there as well, probably from 1.3 to 1.1. So you've run your analysis and you found out that the slope, the safety factor for your global stability is below the minimums. How do you fix it? How do you change your wall design to address that and maybe get your safety factor to a higher level? There's multiple ways to do it. You can do the increase the grid length, as we have in this picture here. It was originally this length, and then we've extended it to intersect with that slip surface and potentially push it farther into the hillside, giving you a larger safety factor. Another way to do that is to maybe bury more block, doing the exact same thing, pushing it into the hillside, giving you a higher safety factor. Other ways to do it is maybe strengthen the geogrid, because if the slip surface is coming through your wall and intersecting with grids, maybe you just need to beef up that strength so it'll just push it outside that wall zone. Then you also have the option to increase the infill soil. as that is the one thing you most likely have control over. If you used the on-site soils and if it was a clay, you might want to recommend doing an engineered soil or engineering material that is a higher friction angle, gives you a little bit more stability and allows for that slip arc or slip surface to go beyond the wall and into the surface, to the hillside a little bit more. So those are a few options. You can always play around, see which one's best for your site. There's no right or wrong answer. It's just a combination of which one's more efficient for your particular project. It could be a combination of them or just one as you go. All right. What if you've exhausted all those efforts and you still have an issue? The slope stability is still not enough to pass your safety factors. So that sometimes means it's a weak soil. And if you find out that it's because of poor soils or weak foundations, what do you have to do to solve that? Most likely, you're going to reach out to the geotech and they're going to have to determine how to solve that foundation problem, and usually doing foundation improvements. So that usually has to happen before the wall is built, just to ensure everything's hunky dory on your site. So always communicate between the two of you, between the wall designer and the geotech. Maybe they're the ones doing the wall design as well. So you might all be working together. It's always good to have clear communication streams between everybody. All right. So AB Walls, I've kind of mentioned our design software a lot. Uh, it does not do global stability. It does do ICS, which is pretty darn close, but it doesn't do global. There's plenty of global stability softwares out there. One particular one is RISA. It's created by Adama Engineering, and what AB Walls is capable of doing is exporting your section design to RISA, and so that way it'll do all of the geometry that you've already done in AB Walls: height, grid lengths, slopes, surcharges, depths of buryment. All of that will be imported into RISA. So all you have to do is maybe make a couple of minor tweaks, confirm what's been put in, and run the analysis and see what's going on. We've had that in the program for quite a while. But if you're just new to the industry, or you don't have RISA, or you'd like to get into that, or you have questions and like to be shown that, just let us know. We have done a couple of one-on-one tutorials with engineers on how to export and import into RISA to run global analysis. Um, there are plenty of other softwares out there that do it. That's the only one we have export capabilities to. RISA Plus is also another one. The difference between RISA and RISA Plus is that RISA Plus now has limit equilibrium methodology and therefore designing the retaining walls. And I'll get into that a little bit later here. Any questions on global stability before we move on? All right. If you do have any, just throw them in the questions area and I'll try and answer them as I go. Otherwise, I'll catch them at the end. So now we're going to move on to terraces. Similar concept. We still have that quick reference detail at the beginning of the book, giving you the quick notes for reference for designing terraces. But we'll go into the chapter here in depth. So, first thing is you want to design your terraces. How do you design them properly? First thing you want to do is we have some rule of thumbs out there on how to design terraces. So I'm going to go as if you're plugging it into our AB Walls design software. I'm pretty sure that there's plenty other softwares out there. I'm not sure any of them at the moment do full terrace designs outside of global stability programs. But for the standard retaining wall design software, you're going to follow the same concepts. So the first thing you're going to do is you're going to design the grid length for your lower wall to be 60% the total grade change. So your total terrace structure height, you're going to have 60% that height as your grid length for your lower wall. So if you have two 6-foot tall walls, so two 2-meter walls, you're going to put 60% of those heights, so 12 feet or 4 meters, as a grid length in your wall for your lower structure. And then if you have multiple tiers beyond just two, you're going to do the same concept for those subsequent tiers all the way up. And then you're going to apply the upper walls as surcharges to your lower walls. And how do you determine what surcharge needs to be added? First, when you're getting into the surcharge aspect, you're going to find out is this wall actually being applied as a surcharge or not? Um, First, you want to find out what is the spacing between your two walls. Is it twice the height of the lower wall? If so, then those two walls are technically not in a terrace application and they can be designed as independent structures. As you can see in the top left of my image, twice the height back essentially makes them two different structures. If they are closer, which you do have the option to do them closer because you'll be designing them, uh, then you can apply that upper wall as a surcharge to the lower wall. To calculate what the surcharge value should be is you're going to take the height of the upper wall or walls, depending on how many you've got, and then you're going to times it by the soil weight, unit weight, or the density of that soil, and that's going to give you a value. So if you've got a 4 foot tall wall and it's 120 pounds, you're going to apply 480 to the top of your lower wall as to represent that upper structure. And then if you've got more and more walls, the taller they are, uh, you've got a little bit more surcharge to throw on there. So once you've got the terrace walls designed, we do recommend global stability be run for terrace structures. But again, as the engineer of record, that is your decision to make based off of your knowledge of the site and the materials being used. Again, I'll be redundant in this, just like our best practices is, because I want to drive some points home here. You are the controlling engineer on these sites. If you feel like global stability is a concern, let people know and see if you can get that run, either by you or by the geotech. It doesn't matter what our paperwork says. If our best practices says you have to, again, it is your decision. We do not override your decision because you will know it a lot better than we do. All right. So, also, that note, I should say that those previous rules of thumb I just said, grid length 60% and the surcharge applied for the upper structures, those don't negate the need for global stability. By adding those, by following those rules, you're pretty close to a stable structure, but terrace structures do are one of those considerations to say we should look at global stability if that's the case. So they don't remove that need to look at global stability. They just get you that much closer to being a stable wall. So if you've got a terrace structure and you've run the analysis and you found that the slip arc, as in the left image here, is running through your wall and the safety factor is still below the minimum, the some solutions to do that to get that stability increased so that way you can push that farther into the hillside. The same four as before: increase the grid length, increase the grid strength, change the soil strength, so get in better soils, bury more block. Those all still apply for terrace structures. But since there are multiple structures on one, you do have a few more options. You could increase the spacing of the tiers. I can't guarantee this will always solve the issue, but it could help because by spacing these out, you have essentially changed the overall or the effective slope of this site, making it softer and allowing for more larger safety factors on that slip arc. That's a potential. Doesn't always work, and maybe you don't have the room on your site to accomplish that. Those are all things you got to think about. Another option would be to increase the height of the lower wall. If you've got a really short wall and then a tall wall on top of it, you might want to even them out a little bit better, unless you've got other design choices that are limiting those heights. That could also improve global stability. Again, can't guarantee that because every site is different, soils are different. You don't know what's going to happen, but those are some other things to play around with. All right, so now that you've gotten through the design, you've done the global for a terraced, now it's for construction. Terraced walls have a little bit more emphasis on compaction, mainly because you don't want that settlement to happen between one wall and the next. Mainly because if one wall is sitting on top of the lower wall's infill area, if there's some settlement, you don't know what that settlement can do to the internal stability of that lower wall. Always want to make sure you've got it nice and compacted so there is as little settlement as possible. Um, but the big area when you're doing compaction for terraces is where one wall splits into two. Like I have two pictures here showing that. These ones are essentially for small planters, but I have seen this happen for taller walls and for longer runs. You don't want one wall as soon as it transitions off of the lower wall to start to settle, because then that's a differential settlement, and it could cause aesthetics problems, cracks in the walls, and um, to the extreme, some stability concerns, mainly of the localized wall, not global, but you still want to make sure that you've got good compaction in those areas to eliminate or reduce any differential settlements at that point. All right. I've gone through global analysis and uh, terraces. Uh, AB Walls, at the moment, does not design terraces. I'm not sure of any program out there beyond global stability programs that can do terraces, but what we're going to have coming up in next year, in 2020, is we're going to be throwing in AV walls, the LEM or limit equilibrium methodology into AV walls, which does give us the option to do terrace structures. As you see, I've got a couple of visuals here showing that. They could be evenly spaced, they could be farther set, they could be really tall walls, all depending on your site. This is a feature that's awesome that comes with the LEM function of the software. And it also allows you to do slope below the wall. First time the software will have that in there as well. Um, this is coming soon, hopefully in 2020. If you want to know more about it, I'm going to go a little bit more into LEM here soon. But this one also will be exportable to RISA, a global stability program, so or RISA Plus anyway. So that way, if you do it in a terrace application in AB walls and you want to analyze it, you don't have to recreate that geometry. It's already done for you, just like it is already in our regular AB walls. But when you get into the LEM portion, uh, this will count as well. All right, so what is LEM? I said I'd get into it, so here we go. LEM is a global stability like, air quotes, like analysis to determine the internal stability or the accuracy of your internal stability. It is a better, there's more calculations, more analysis, better overall view of what's happening inside your internal stability. It was created by Dovlashinsky, and it has been recently adopted by the FHWA, AASHTO, and NCMA as a viable alternative to our traditional internal design calculations. Not that you don't have to do the traditional, you still can. This just gives you a little bit more in-depth look of it. And the great thing about it being adopted by so many different codes, methodologies, and associations is that now you can, instead of having to remember all those different codes and idiosyncrasies or intricacies of every code and design, uh, you now can do it in just one that is accepted by all, which is great. We'll find that to be hopefully very helpful in the years to come, and hopefully as we learn more about these walls, because it's always adapting and changing on us. It's good to have everybody on the same page. All right. So the main goal of LEM is to expand on the ICS model and bring an even higher level global stability analysis to the internal design process. We have a chapter dedicated to it in our engineering manual. Just like ICS, it's going to be in our engineering manual, and I'll send you a link to that in our follow-up email tomorrow so you can read up more on it. We also went into a quick reference informational tech newsletter that we had a couple years ago, so you can also reference that. And as soon as it's out in AB Walls, we'll be having our own ABU online webinar just like this to get you more in depth on LEM, AB Walls, and any questions you have in 2020. All right. As a quick review, as I'm going to go through this review here, if you guys have any questions or knowledge you want to impart, please put it in the question box, and we'll see if I can answer it or share it with everybody. All right, so went through review here. We gone through defining the global stability. We had a video and also definitions. We went through identifying situations where it could be global stability could be a concern, and solutions on how to increase stability so it's not that big of a concern. Then we also went through terrace wall designing, global stability, and upcoming sneak peek to our AB walls. All right, I have a question. Will LEM replace internal stability checks? That depends, Sharon, on what you want to design it for. You'll still have in AB walls are standard, the traditional internal and external checks for your stabilities. However, this will be a separate module, kind of similar to our ICS, where you can run LEM on specific sections to see if that stability is acceptable to you. I think at some point verge into um, it might verge into being the only one you have to run, but that's all up to how the industry keeps changing on us. So at this moment, you still can do the traditional, then do the LEM, but at this point, um, it's not the only calculation you run. Did I answer your question? I hope. If I need to go a little bit more in depth, let me know. I'll get somebody else involved on this. All right, perfect. All right, so we've gone through everything. If you've got more questions, throw them in here. I'm just going to give us a little preview of next month. Next month, we're going to be finalizing our best practices series, where we're going to the above wall considerations. This is just going to dive a little bit more into fences, slopes, chapter 12 of our best practices. That'll be on September 26th, and we'll have our 3 sessions, 10, 2, and 4 p.m. is Central Time. Uh, I don't see any new questions coming in, but I'll stay on here for a few more minutes. I want to thank everybody for showing up. If you do have questions, throw them in there. If you leave by then and you think of something, don't hesitate to give me an email or respond back to my email that I'll send you guys out tomorrow with the evaluation form, PDF of these presentations, video link, and some quick links to other items that I mentioned. Do you need to know my name? You certainly can. My name is Laura Horstman. I'm an engineer with Allen Block here at the moment. I hope to stay here for as long as I can. And if you have any questions, I'm a good contact if you need. All right. Thanks again for everybody who attended, and I'll just stick around a couple more minutes to see if anybody's got any more questions. All right. Thanks for everybody for staying around and attending. I will be sending that email out tomorrow. I'm going to end this meeting now, but if you have any questions or you come up with one, don't hesitate to reach out to us. Thanks again for everybody, and have a great day.